you have learnt Green's theorem. So the Green's theorem is the m of xy and n of xy are two continuous functions of x and y. Then the derivatives dou m by dou y and dou n by dou x are continuous partial derivatives in x. Continuous partial derivatives. Then integral over c m dx plus n dy equal to double integral over r dou n by dou x minus dou m by dou y dx dy, where c is the closed curve. The closed curve is enclosed by a region R. The region R is enclosed by a closed curve. So, in the xy plane, can you see my board?
Yes, ma'am.
So, in the xy plane, this is a closed curve. C is a closed curve. The region is R. The R is the region enclosed by the curve C. So, in that closed curve C, Mn are two functions. Then integral over C m dx plus n dy equal to double integral over R dou n by dou x minus dou m by dou y dx dy. Using this Green's theorem, now we prove the Cauchy's integral theorem. So let us see what is Cauchy's integral theorem. Let a function f of z is analytic and f dash z is continuous at each point inside and on a closed curve C, then integral over C f of z dz equal to 0. So the Cauchy's integral theorem is f of z is analytic function and f dash z is continuous at each point. At each point means where inside the closed curve C and on the closed curve C. On every point of the closed curve and inside every point of the closed curve, f dash z is continuous. So f dash z is continuous at every point on this curve C and inside the curve C. Then integral over C f of z dz equal to 0. This is the Cauchy's integral theorem. Now we prove this theorem. Okay. So what is Cauchy's integral theorem? F of z is analytic function and f dash z is continuous. Then integral over C f of z dz equal to 0. So now let us prove this. Proof. Let z equal to x plus iy, f of z equal to u plus iv, then dz equal to dx plus idy. You know this. Z equal to x plus iy, f of z equal to u plus iv. Now integral over C f of z dz equal to integral over C f of z means u plus iv, dz means dx plus idy. So integral multiplying all these terms u dx plus u into I dy, ui dy plus I into v dx, iv dx plus I square means minus 1 into v dy. Separating the real and imaginary parts, u dx minus v dy plus I into u dy plus v dx. Is this okay? I am going to the next slide. Is this okay?
Yes, ma'am.
Next, integral over C f of z dz equal to separating real and imaginary parts. Integral over C u dx minus v dy plus I integral over C u dy plus v dx. Now, using the Green's theorem, what is Green's theorem? Integral over C m dx plus n dy. What is the Green's theorem statement? Already you know that. Now I have given you the integral over C m dx plus n dy. It can be written as double integral over R dou n by dou x minus dou n by dou y dx integral over u dx minus v dy. How can you write this? Tell me. So using this Green's theorem, how can you write this integral?
Double integral dou v
Double integral over
dou v by dou y
minus is there. Minus dou v by dou x.
dou v by dou y.
In the place of n, we have minus v.
So dou v minus dou v by dou x
Minus
minus dou u by dou y.
dou u by dx dy. Is this okay?
Yes.
This is the statement of Green's theorem. In the place of n, you have u. In the place of n, you have v. So dou n by dou x. అంటే dou of minus v by dou x. అంటే minus dou v by dou x minus dou u by dou y dx dy. That is the first part. Already I have wrote. Next. Last line. Can you see the last line?
Yes, madam.
Integral over c u dy plus v dx. u dy plus v dx. లేదంటే v dx plus u dy. How can you write this? Using this theorem. How can you write this? In the place of n, you have u.
Dou u by dou x minus dou v by dou y minus dou v by dou y.
dx dy. So that is the that is in the PPT. Now you understand the second line. Double integral minus dou v by dou x minus dou u by dou y dx dy plus I into double integral dou u by dou x minus dou v by dou y dx dy. Do you understand this?
Yes, madam.
Leela, what about you?
Yes, madam.
Okay. Now using Cauchy-Riemann equations, Vx means minus Vx means uy. Uy equal to minus Vx. Dou v by dou x means Vx minus Vx means uy. Okay, dou u by dou y. Look at the PPT. Minus dou v by dou x means dou u by dou y. Dou u by dou y write down as it is, and dou u by dou x means dou v by dou ux equal to vy. So ux dou u by dou x equal to vy dou v by dou y. So the two terms vanishes. The two terms are 0. So 0 plus I times 0, that is equal to 0. So integral over c f of z dz equal to 0. Okay. Okay, do you understand?
Yes, madam.
I am going to the next one. First, integral over c f of z dz. F of z means u plus iv into dz means dx plus I dy. Multiplying all these terms and separating your imaginary and real parts. After that, using Green's theorem and applying Cauchy-Riemann equations, you will get 0. Okay. Next. Extension of Cauchy's theorem for multiply connected regions. So there are more than 2 regions. Then how can Cauchy theorem applies? So let C1 and C2 are two simple closed curves, and f of z is analytic in the region or between these two curves. Then so C1 and C2 are So let C1 and C2 are two simple closed curves. We have two simple closed curves, C1, C2. And f of z is analytic in the region or between these two curves. So this R is in between these two curves. This is R. R is the region between these two curves. And f of z is analytic in this region. Then integral over C1 f of z dz equal to integral over C2 f of z dz. That is the extension of Cauchy's theorem. Two simple closed curves are there and f of z is analytic between these two regions. Okay. F of z is analytic between these two regions. Then integral over C1 f of z dz equal to integral over C2 f of z dz. This is the extension of Cauchy's theorem. Next, Cauchy's integral formula. Next topic is Cauchy's integral formula. Using this formula, we have to do so many problems. So, the Cauchy's integral formula is f of z is analytic function everywhere on and within a closed curve C. If z equal to a is any point within C, then f of a equal to 1 by 2 pi integral over C f of z by z minus a dz. So, f of z is analytic. Everywhere. Everywhere means what? On the closed curve C and within the closed curve C. So, f of z is analytic on at every point on a closed curve C and at every point within the closed curve C. Within the curve and on the curve. So, f of z is analytic at every point on the curve and within the curve C. Then, and f z equal to a is any point within C. So, z equal to a is a point. A is a point within C. Then, how can you write f of a equal to 1 by 2 pi integral over C f of z by z minus a dz. So, this is the Cauchy's integral formula. Very, very important formula. So, what is the statement? F of z is analytic function where at every point on a closed curve C, at every point on a closed curve C, and at every point within the curve C, z equal to a is any point within C. Then f of a equal to 1 by 2 pi integral over C f of z by z minus a dz. This is the Cauchy's integral formula. Now we will prove this. Okay, let us see how can you prove this. Let us see the proof. Let f of z is analytic within a closed curve C. Z equal to a is a point within C. So, given that f of z is analytic within a closed curve C and z equal to a is a point within C, choose a small circle C0 with center A such that C0 lies within C. So, look at the diagram. Is it audible?
Yes, ma'am.
Is there any disturbance?
No, ma'am.
Okay. So, C is a closed curve. Not only circle, it is a closed curve. Generally, I am writing the circle. Any closed curve, C is a circle. And f of z is analytic within a closed curve C. So, f of z is analytic at every point of the curve C. Z equal to a is a point. So this is the point z equal to a. And choose a small circle C naught such that, so choose a small circle C naught with center A. C naught is a circle, small circle within C with center A, such that C naught lies within C. Next, consider a function f of z equal to, consider a function f of z by z minus a. This is analytic at every point except at z equal to a. So this is analytic function because f of z is analytic, and so f of z by z minus a is also analytic function at every point except at z equal to a. So at z equal to a, it becomes denominator is 0. So it is not analytic at z equal to a and analytic at every point. So this function is analytic between C and C naught. So this is not analytic. F of z by z minus a is not analytic at z equal to a, but it is analytic except every point. So it is analytic at in the region between C and C naught. So it is not analytic at z equal to a, but it is analytic at every point. That means it is analytic between C and C naught in the region R. So using extension theorem, so integral over C f of z by z. What is extension theorem? What is extension theorem? If f of z is analytic between two regions C1 and C2, then integral over C1 f of z dz equal to integral over C2 f of z dz. Now, this is the extension of Cauchy's theorem. Now, applying this theorem, integral over C f of z dz equal to integral over C naught f of z dz. Applying this theorem, this is equation number 1. Now, consider a point z minus a in C naught. So, z minus a can be taken as z minus a equal to r e power I theta, dz equal to, differentiating with respect to theta, dz equal to r e power I theta into I d theta. Theta varies from 0 to 2 pi. Since C naught is a circle, so theta varies from 0 to 2 pi. So integral over C naught f of z by z minus a dz equal to integral over C naught f of z by z minus a dz equal to, so integral theta equal to 0 to 2 pi f of z means a plus r e power I theta, z minus a. What is the point you have taken? Z minus a equal to r e power I theta. That means z equal to a plus r e power I theta. dz equal to a is constant 0, r e power I theta into I d theta. We are differentiating with respect to theta. So e power I theta into I d theta. Theta varies from 0 to 2 pi because it is a circle. C naught is a circle. So the angle moves from 0 to 360 degrees. Now, using these conditions, integral over C naught f of z by z minus a dz equal to integral theta equal to 0 to 2 pi f of z means what? A plus r e power I theta by z minus a r e power I theta into dz r e power I theta into I d theta. Now r e power I theta cancels out, I common out. So what is the remaining function? Integral theta equal to 0 to 2 pi f of a plus r e power I theta d theta. Now, as r tends to 0, r means radius. If the radius tends to 0, If the radius tends to 0, C naught is a circle with center A. If the radius, this is the radius. If the radius tends to 0, radius becomes small, going to small, then it reaches to the center. If the radius shrinks. If the radius become going small, then if the radius, so this is the radius A, C naught. Radius becomes small, small, small. Then it reaches to a point, center A. So if R tends to 0, the circle C naught shrinks to the point A. So as R tends to 0, integral over C naught f of z by z minus a dz equal to, so you put R equal to 0. So integral theta equal to 0 to 2 pi f of a d theta. R 0 means f of a d theta. So what happened? PPT is not moving. Okay. Are you operating PPTs?
No, ma'am.
So integral over c f of z by z minus z is equal to I into f of a is a constant, f of a common out, integral d theta means theta 0 to 2 pi. So I into f of a into 2 pi. So I into 2 pi moves to the left side. So 1 by 2 pi integral over c f of z by z minus z is equal to f of a. So f of a equal to 1 by 2 pi I integral over c f of z by z minus a dz. So this is the Cauchy's integral formula. Very, very important formula. Now let us see once more this one. Now, once again we will look at this. F of z is analytic function everywhere. That means on and within a closed curve C. Everywhere means within the curve C and on the curve C. And z equal to a is a point within C. Then f of a can be written as 1 by 2 pi integral over C f of z by z minus a dz. Now let us see the proof. So f of z is analytic within C. Z equal to a is a point within C. Choose a small circle C naught with center A such that C naught lies within C. After that, consider a function f of z by z minus a. This is analytic everywhere except at z equal to a. So at z equal to a, it is not analytic, and analytic everywhere. So it is analytic between C and C naught. So by Cauchy's extension theorem, integral over C f of z dz equal to integral over C naught f of z dz. ఇందో లేలా
ఎస్ మేడం.
ఇక్కడ మీరు ఒక్కసారి నోట్స్ రాసేటప్పుడు ఇది ఇంటిగ్రల్ ఓవర్ సి బై Cauchy's extension theorem f of z by z minus z dz equal to it రాసుకున్నాం. Now the function is f of z by z minus z, not f of z. Our function is f of z by z minus z. So this function is analytic between c and c naught. So try to make a small correction. Okay, do you understand?
ఎస్ మేడం.
ఈక్వేషన్ 1 దగ్గర by z minus a రాయండి నోట్స్ రాసేటప్పుడు.
ఓకే మేడం.
ఇక్కడ ఓన్లీ f of z ఉంది, మీరు f of z by z minus a రాయండి. Now z minus a equal to r e power I theta. So by integrating this forces with respect to theta, you can get I into f of a into 2 pi. That is that from that f of a equal to 1 by 2 pi I integral over c f of z by z minus a dz. Okay, let us go to the next one. Morero's theorem, converse of Cauchy's theorem. So Morero's M-O-R-E-R-A, that is R, M-O-R-E-R-A, Morero's theorem. M-O-R-E-R-A-S, that is converse of Cauchy's theorem. What is Cauchy's theorem? What is Cauchy's theorem? If f of z is analytic within c and on the c, then integral over c f of z dz equal to 0. That is Cauchy's theorem. If f of z is analytic within c and at every point on the c, then integral over c f of z dz equal to 0. This is Cauchy's theorem. Now inverse, the converse means if integral over c f of z dz equal to 0, then f of z is analytic. Now we have to prove that f of z is analytic. So given that integral over c f of z dz equal to 0, now we have to prove that f of z is analytic. Now look at the statement. If f of z is continuous in a region of and integral over c f of z dz equal to 0 around every simple closed curve c, then f of z is analytic in R. So given that integral over c f of z dz equal to 0 around a closed curve c, then f of z is analytic. So we have to prove that f of z is analytic. For that, let integral z naught to z f of z dz equal to capital F of z. My integral over total curve f of z dz is 0, but we are taking two points z naught and z. So integral z naught to z f of z dz equal to a capital F of z. Let us assume where small f of z equal to u plus iv, capital F of z equal to p plus iq. Z naught is a fixed point and z is a variable point. I am going to the next. So capital F of z equal to integral z naught to z f of z dz. So this is capital F of z. Already we have seen the previous slide. So capital F of z equal to integral z naught to z f of z dz. So f of z means u plus iv, dz means dx plus idy. So let f of z equal to p plus iq. Capital F of z equal to p plus iq. Capital F of z is a complex function. We assume it as p plus iq. By multiplying all these terms, u plus iv into dx plus idy, right? And separating real and imaginary parts, u dx minus v dy plus I into v dx plus plus what? U dy, isn't it? U dx plus I square minus v dy. I common out v dx plus u dy. So comparing real and imaginary parts, p equal to, this is p plus iq. So comparing real and imaginary parts, p equal to
u dx minus v dy.
u dx. Can you look at the bottom line?
Yes, madam.
P equal to u dx minus v dy. Q equal to v dx plus u dy. So this is P and Q. And now look at the PPT. Dou P by dou x. There is a small mistake. No integral symbol. P equal to, okay. Okay. Integral, sorry. Integral is okay. Integral u dx. Integral v dx plus u dy. Now dou P by dou x. So we are differentiating both with respect to x. So dou P by dou x equal to differentiation integration cancel out and u remains. And dou P by dou y minus v. Dou Q by dou x v. Integration differentiation cancel out, v remains. And dou Q by dou y u. Now using Cauchy-Riemann equations, dou P by dou x equal to dou Q by dou y. Because what are Cauchy-Riemann equations? Ux equal to, what are Cauchy-Riemann equations?
ux equal to
Ux
vy
equal to
Ux equal to vy, uy equal to minus
minus
vx. Now apply PQs. Apply Cauchy-Riemann equations for PQ. Px equal to qy, py equal to minus qx. Px means dou p by dou x equal to dou q by dou y. Dou p by dou y equal to minus dou q by dou x. Now using Cauchy-Riemann equations, dou p by dou x. So f dash z. 1 minute. Let us go to the previous slide. Now using this dou p by dou x equal to, which are equal, dou p by dou x u, and where is u? Dou q by dou y. So dou p by dou x equal to, both are u. Dou p by dou x equal to u, dou q by dou y equal to u. So dou p by dou x equal to dou q by dou y, and dou p by dou y equal to minus dou q by dou x. So p and q satisfies Cauchy-Riemann equations. That means f of z equal to p plus iq is analytic function. F of z, since PQ satisfies Cauchy-Riemann equations, f of z is analytic function. So how can you write f dash z? Dou p by dou x plus I into dou q by dou x. Dou p by dou x is u. Already we have written. Dou q by dou x is v. U plus iv, that is f of small f of z. Since capital F of z is analytic, its derivative small f of z is also analytic. So we have to prove that small f of z is analytic. Already we have proved it. What is the condition you have to prove? Small f of z is analytic. So that is we have proved. So look at 1 second. So what is Morera's theorem? If integral over c f of z is equal to 0 around every simple closed curve c, then f of z is analytic. So given that integral over c f of z is equal to 0, we have to prove that f of z is analytic. For that, we have taken capital F of z equal to integral z naught to z f of z dz. Let us assume that capital F of z equal to p plus iq. Small f of z equal to u plus iv. Next, by multiplying f of z and dz, u plus iv into dx plus I dy, and comparing real and imaginary parts, p equal to integral u dx minus v dy, q equal to integral v dx plus u dy. Dou p by dou x, differentiating with respect to x. And d by dx of integration means d by integration differentiation cancel out, u remains. So dou p by dou x equal to u, dou p by dou y equal to minus v, dou q by dou x equal to v, dou q by dou y equal to u, which are equal. Dou p by dou x equal to dou q by dou y, since both are u. And dou p by dou y equal to minus dou q by dou x. That means PQ satisfies Cauchy-Riemann equations. That means f of z equal to p plus iq is analytic. So f dash z equal to dou p by dou x plus I into dou q by dou x. So that is u plus iv. So small f of z. So capital F of z is analytic and its derivative small f of z is also analytic. So that is the condition we have to prove. Next, singular point. What is meant by singular point? A point at which the function f of z is not analytic is called a singular point. If a function is not analytic at a point, then that point is called singular point. Next, let us look at the note. If the point z equal to a lies within the curve or on the curve, then integral over c f of z by z minus a dz equal to 2 pi I into f of a. This is Cauchy's integral formula. When we apply Cauchy's integral formula, the point z equal to a may lies within the curve c or on the curve c. Then you can apply Cauchy's integral formula. If the point z equal to a lies outside the curve, then integral over c f of z by z minus a dz equal to 0. So if the point z equal to a lies within c or on the c, then integral over c f of z by z minus a dz equal to 2 pi f of a. If the point lies outside the curve c, then the integration is 0. Now using this formula, let us go to the problems. Evaluate integral over c e power 2z by z minus 1 into z minus 2 z dz, where c is the circle mod z equal to 3. So what is the given function? Integral over c e power 2z by z minus 1 into z minus 2 dz. So this is the given curve, given integration, and the given circle is mod z equal to 3. Now we have to find this integral value. So given function f of z equal to e power 2z. So f of z equal to e power 2z. If z equal to 1, then denominator is 0. Then the function is not analytic. So at z equal to 1, function is not analytic, and z equal to 2. The function is not analytic because the denominator is 0. So they are singular points. So see, to get the singular points, let the denominator is 0. Singular points implies z equal to 1, z equal to 2. If z equal to 1, then denominator is 0. Z equal to 2, denominator is 0. So if z equal to 1 and z equal to 2, the function is not analytic. And given circle, mod z equal to 3. This is C. Mod z means x plus iy equal to 3. Modulus means root of x square plus y square equal to 3. Squaring on both sides. X square plus y square equal to 9. Now let us check whether these points lie within the curve or outside the curve. First let us check. This is the given circle C. Now we have to check these singular points lies within this curve or outside the curve. For that, z equal to 1 means 1 comma 0. Isn't it? What is the real part? 1. Imaginary part 0. 1 means you can write this 1 plus I into 0. That is 1 comma 0. Substituting this 1 comma 0 on this curve, substituting x square 1 square, y square 0 square, that is 1. So what the LHS is 1. What is RHS? 9. So 1 less than 9. So the point z equal to 1 lies inside the circle. Okay. So this is the given circle x square plus y square equal to 9. Now we have to check these two singular points lies within this curve or outside the curve. For that, substitute these points on this curve. Z equal to 1 means 1 comma 0. Substituting 1 comma 0 on this curve, 1 square plus 0 square, that is 1 less than 9. So z equal to 1 lies within the curve, within the circle. 1 lies within the circle. Similarly, let us go to the point z equal to 2. So z equal to 2 implies 2 comma 0. Substituting on the circle, 2 square plus 0 square, 4 less than 9. Less than 9 means this point also lies within the circle. So these 2 points lies within the circle. So you can apply Cauchy's integral formula. Now let us go to the next part. First we have to separate the fractions. Given, so consider z minus 1 into z minus 2. You have to separate the fractions. That means you can take a by z minus 1 plus b by z minus 2 partial fractions. You can use that model, or simply you can separate using a and b. Without using a and b, you can simply separate. So take the denominator as it is, z minus 1 times z minus 2. The numerator is 1. Now the numerator is 1. So 1 can be written as using addition or subtraction of these two factors. Now let us take z minus 2 minus z minus 1. No, z minus 1 minus z minus 2. What is the value? Z cancel out. Minus 1 plus 2. Minus 1 plus 2 means
Plus.
so the total numerator is 1. Is it okay?
Yes, madam.
This method is not applicable for all the times. If the numerator can be written as the sum of denominator terms, then you can apply this method. For all the terms, it is not applicable. Now, the numerator is 1. So, 1 can be written as subtraction of these two terms. If you subtract these two terms, you can get 1. Do you understand this step?
Yes, ma'am.
Madam.
What is the numerator value finally? What is the numerator value?
E power 2z.
No. In this step.
Madam.
In this step, z cancel out. Minus 1 plus 2. That is 1. So this 1 is written in this form. Now, separating the factors, z minus 1 by z minus 1 into z minus 2. You please mute your mobiles. If any doubt, you can call me. Ramya, mute your mobile. Separating the factors, z minus 2 by z minus 1 into z minus 2. Separation of fractions means you have to separate the numerator only, not the denominator. You should write the denominator for every total denominator for every term. You have to separate only numerator. Now z minus 1 cancel out, z minus 2 cancel out. 1 by z minus 2 minus 1 by z minus 1. If you take a by z minus 1 plus b by z minus 2 also, you get a as minus 1 and b as 1. If you don't understand, you can go by this method. A by b by, you can go by that method. So 1 by z minus 1 into z minus 2 can be written as 1 by z minus 2 minus 1 by z minus 1. So that is 1 by z minus 2 minus 1 by z minus 1. Now integral over c e power 2z by z minus 1 into z minus 2 dz equal to integral over c e power 2z into 1 by z minus 2 minus 1 by z minus 1 dz. So separating the integration, e power 2z by z minus 2 dz minus integral over c e power 2z by z minus 1 dz. So 1 by z minus 1 into z minus 2 can be written as 1 by z minus 2 minus 1 by z minus 1. Multiplying e power 2z and separating the integration. So this is in the form of integral over c f of z by z minus a dz. This is in the form of integral over c f of z by z minus a dz. Okay. Now what is a here? Now what is a? 2. Z minus a. A is 2. So the 2, z equal to 2 lies within the circle. Already we have verified that. Z equal to 2 lies within the circle. So you can apply Cauchy's integral formula. So applying Cauchy's integral formula, 2 pi I into applying Cauchy's integral formula, 2 pi I into f of a. Here a is 2. 1 also lies within the circle. So applying Cauchy's integral formula, 2 pi I into f of 1. A is 1. What is f of z? We know that f of z equal to e power 2z. So f of 2 means e power 2 into 2, e power 4. F of 2 means e power 2 into 2, e power 4. F of 1 means e power 2 into 1, e power 2. So 2 pi I into, so what is the answer? 2 pi I into f of 2 minus f of 1, e power 4 minus e power 2. So that is the answer. So first we have to find the singular points. So for that you have to take the denominator equal to 0. Then you can get singular points. And you have to check whether the singular points lies within the circle or outside the circle, or lies within the curve or outside the curve. and then you have to separate the fractions, and then you have to get the given integration into the form of integral over c f of z by z minus a. Now a equal to 2 lies within the circle, so 2 pi I into f of a, f of 2. Here also 2 pi I into f of 1, f of 2, okay, e power 2 into 2, e power 4, e power 2 into 1 is square. Okay, now I am going to the PPT visible.
Yes, madam.
Yes, ma'am.
Okay, next problem. Let us look at the next problem. Do you understand first problem?
Yes, ma'am.
Yes, madam.
Okay, next. Integral over c e power z by z minus 1 into z minus 4 dz, where c is the circle mod z equal to 2. Look at this one. If you don't understand, I will tell you. Look at this one for 2 minutes. If you said okay, then I will go to the next slide.
Okay, madam. Okay, madam.
I am going to the next slide. What are the singular points here?
1, 4.
Okay, look at this one. Mute the mobiles. If you want to say anything, then unmute. Otherwise, mute. Now, 1 by z minus 1 into z minus 4. This can be written as a by z minus 1 plus b by z minus 4. You can use that method, or without using that method, you can simply go in this method. Z minus 1 into z minus 4. Now, what is the numerator? 1. So, if you subtract these two terms, z minus 1 minus z minus 4, z cancel out, minus 1 plus 4, 3. You have 3 turned out, but the numerator is only 1. But we got 3 here. So if you take 1 by 3 here, so here you have 3, 3 by 3 is 1. 1 by z minus 1 into z minus 4. So 1 by 3 into z minus 1 by z minus 1 into z minus 4 minus z minus 4 by z minus 1 into z minus 4. So 1 by 3 into z minus 1, z minus 1 by z minus 4 minus 1 by z minus 1. So if you go on the AB method also, you will get A is minus 1 by 3, B is plus 1 by 3. If you can't understand this, you can use that method, A by z minus 1 plus B by z minus 4. Next. Now, the singular point z equal to 1 lies within the circle and z equal to 4 lies outside the circle. Now, let us go to the given integral. So, what is the given integral? Integral over C. E power z by Now look at the PPT. 1 by z minus 4 into z minus 4 written as 1 by 3 into z minus 4 minus z minus 1. Separating the integration, e power z by z minus 4 minus e power z by z minus 1. So 4 is a point outside the circle, so the integration is 0. 1 is a point inside the circle, so you can apply Cauchy's integral formula for 2 pi I into f of 1, okay, e power 1. So 1 by 3 into 2 pi I e. So that is the answer. Okay, I am going to the next. Third problem is also same model. You can look at that after the class. Let us go to the fourth problem. Now let us go to the fourth problem. Evaluate integral over c sin pi z square plus cos pi z square is by z minus 1 into z minus 2 z, where mod z equal to 3. So the given curve is mod z equal to 3. The given function is sin pi z square plus cos pi z square. So singular points z equal to 1, z equal to 2. By expanding mod z equal to 3, you will get x square plus y square equal to 9. Now separate the fractions. 1 by z minus 1 into z minus 2. By separating, we get 1 by z minus 2 minus 1 by z minus 1. Now check whether the points lies within the circle or outside the circle. 1 means 1 comma 0. Substituting on the circle, 1 square plus 0 square 1 less than 9. So lies within the circle. Z equal to 2 means 2 0. 2 square plus 0, 4 less than 9. So both points lies within the circle. Now separating the factors, integral over c sin pi z square plus cos pi z square by z minus 1 z minus 2 z is equal to, the numerator is f of z. Separating f of z by z minus 2 minus f of z by z minus 1. What is f of z? Sin pi z square plus cos pi z square. So 2 pi I into f of 2 minus 2 pi I into f of 1. F of 2 into sin pi into 2 square, pi z square. Z is 2. Kept sin pi into 4 plus cos pi z square, pi into 4 minus sin pi into 1 square, 1 minus cos pi into 1. Sin 4 pi plus cos 4 pi minus sin pi minus cos pi. Sin 4 pi is 0, sin pi is 0. Cos 4 pi is 1, cos pi is minus 1. So 1 minus minus 1, 1 plus 1, 2, 2 into 2 pi, 4 pi I. So this is the fourth problem.